Alright, so if you need to pause the video, read it. That I'll just give you just of it. Here is the bullet. Is 4 grams, going to strike a 200-gram block. It's going to get embedded in it, and then from there, it's going to go across a rough segment, and it's going to come to a stop. The distance that it traveled is 8 meters, and the coefficient of kinetic friction is given as 0.4. Part A wants us to find the net work done on the bullet block system and bring it to a stop. And part B here says what is the speed of the bullet before impact. All right. So the first thing I notice is that here the masses are given in grams, so I'm going to go ahead and convert those units to kilograms. So 4 grams needs to be converted to kilograms, so the ratio between grams and kilogram is 1,000 grams is equal to 1 kilogram. So here's 4 grams, times that by 1 kilogram, divide that by 1,000 grams. The grams cancels out, and then therefore you really have 4 times 1, which is 4 divided by 1,000, which is 0.004 kilograms. And then you can do that same process for the 200-gram block. So make sure to scope out units and stuff like that before you start attacking these values, okay? All right, so I'm just gonna go ahead and convert 200 grams using the same strategy, and that should give you 0.2 kilograms. All right, now that I have the proper units for the bullet and the block, let's go and crack out part A. To find net work on the bullet, I'm just gonna go ahead and use net work is equal to net force times displacement here. And in the diagram, the only force acting on this particular bullet block system and bring it to a rest is the force of friction along this rough segment here, along the rough surface. So therefore, I'm just going to go ahead and break the statement down. So why is this net force? The only force acting on it horizontally in the direction of motion is F of K. And this is displacement here, but in the diagram, it's called D. Well, in this case, it doesn't really matter because the object's moving to the right. So D and delta X have the same value, okay? So here's F of K and then times D. And then from here, I know that F of K by definition is the coefficient of kinetic friction times the normal force. For this one, it's pretty straightforward. The block is sliding across a horizontal surface. So there's an F of G of the system pulling down on it, and then the floor or the surface there is going to push up on it with equal magnitude. So F of N in this case would just be F of G, and F of G would just be mg, but you have to keep in mind it's mass of the whole entire system because now the bullet is stuck inside the wooden block, okay? So here, I'm just going to go ahead and break up F of N is the only thing I don't know. I'm given mu k, I'm given D, D's 8. So I'm going to go ahead and break up F of N into F of G. So they have the same magnitude for this particular problem. Don't always just assume that. This one is pretty straightforward, okay? But F of G, as I stated earlier, is composed of the mass of the bullet plus the mass of the wooden block. Here I just call MB for bullet, MW for wood. And then so it would be mass times gravity. Notice there's a G right there, and times D. So everything I just carried down, except I just broke F of G into mass times gravity, but the mass is the mass of the system. All right, we know everything. Coefficient is 0.4, mass of the bullet is 0.004, and then plus the mass of the wooden block is 0.2. Here, G is negative 9.8, and then D here is 8 because it's given to us. So if you punch all this in your calculator, you should get a value of about 6.4. And it's a negative here because it's work due to friction, or it's work done against the system. So other than that, that is my answer for part A. All right, so let's go and crack out part B. Part B wants us to find the initial speed of the bullet before impact. So here in this diagram, here's V naught or VI, whatever you want to call it. So I'm just going to find that V for you. All right, so in order to do that, you need to set up conservation of momentum. This is the system for impact, aka before collision. So anytime I hear collision, I think of momentum. Here, we're just gonna break it up. Net momentum initially is only contributed to the bullet. So you notice on the left side, I only have initial momentum of the bullet. The wooden block was initially at rest, so I left that out. On the right side, I broke it up into two things because at the end, two objects are moving, the bullet and the block. So I'm just gonna break up on the right side a little more. Okay, on the right side here, you notice here I have the momentum, the bullet final, plus momentum, the wooden block final. However, they are going to move together, so the velocity on the right side is just VF and VF. I did not use VFB or VF wood because they are moving as one, so the final velocity would have to be the same. Okay, so from here, I can just really factor out VF if you want. All right, other than that, left side stays the same. The right side, once again, I factor out VF, so it would just be the mass of the bullet plus the mass of the wind block times the final velocity. And then from here, I'm just going to go ahead and divide both sides by MB just to get VBI by itself, or in this case, my VBI is the same as this V naught in the diagram, right? Because it wants this initial speed of the bullet before impact. All right. So I'm going to go ahead and do a little algebra manipulation by dividing both sides by the mass of the bullet, just to get the VBI by itself. Here, the only thing I highlighted here is VF because it is the only thing you don't know. We know the mass of the bullet, we know the mass of the wooden block, and once again, we know the mass of the bullet on the bottom. So all we have to do is find the velocity of the bullet, velocity of the bullet block system after it, enters this rough segment. Okay. All right. So to find VF, I'm just going to use conservation of, well, not conservation, excuse me, the work kinetic energy theorem, if I can speak. This is an early video. Okay. Here, I just set net work is equal to change in kinetic energy. So I can break up net work is equal to KEF minus KEI. Here, I'm just going to cross out KEF is 0. So once again, I'm going to just focus on the segment here. The final velocity after it slides across this 8 meter is given as 0. So that would be my VF. Well, if VF is 0, my KEF is 0. So what I can do is I can find how much energy was there before it enters this rough segment. If I know this VI was really the VF after the collision. Okay. So I'm just going to break it KEI. I'm just going to carry that negative sign down. KEI is just 1/2. But notice here it would just be the mass of the block and bullet together. Okay. Because once again they are moving together, and then this is VI squared. But keep in mind my VI is really this VF down here because it's VI for the second segment of the problem, but it's the final velocity for the first segment. So it's collision and then it's conservation of kinetic energy, or conservation of what do you keep saying, the work done, not conservation. Okay, I'm sorry. Once again, it's an early video. Here, work is negative 6.4 because I already found that in part A. Here, 1/2 gets carried down. If you add up the mass of the bullet plus the mass of the wooden block, that gives you 0.204, and then VI squared. And so as you can see, the only term I don't know is my VI squared. So if you multiply both sides by 2 and then divide both sides by 0.204, that's what I did there. So 6.4 times 2 is 12.8. And then I need to go ahead and simplify that and then square root it at the same time. So if you take 12.8 divided by 0.204 in your calculator, you should get about 62.75. But you notice here this is VI squared and this is just VI. So what I did too is I radical both sides. So I did two things in one step there. So if you square root 62.75, you should get about 7.92. Okay, so this is how fast the system enter the rough segment. But this VI is the VF after the collision. So really I found this VF. So VF here is 7.92. Now, the other thing you can do, if you don't like to use work kinetic energy theorem to find this VI, you can just use kinematics. VF squared minus VI squared is equal to 2A delta X. Once again, VF is 0 because the block bullet system comes to a stop. So the only thing I do need to find is VI here. I can find A. I know what delta X is. Delta X is 8. So if you break it up here, I just go ahead and carry this work down. And then if you break up A is just simply mu K times G. Now here's the part. If you don't know that A for this particular problem is mu K times G, listen carefully here, and we need to write on your paper. Hopefully you can keep up. Well, if you set up net force is just mass times acceleration. But the only force acting on it is the force of kinetic friction. So you would do F of K is equal to MA, right? But then F of K, you can break up into mu K F of N, and then you can break up Fn into F of G, which is just mg. So really, you have mu K times m times g equals ma. The masses will cancel on both sides, and it leaves you with A is just equal to mu K times g. So if you need to listen to that again, and then hopefully write on your paper to prove that for this problem, A is just mu K times g. Okay, I didn't do it here because I'm running out of space. All right, as you can see here, we know everything. The two coefficients get carried down. Mu K is given as 0.4, G is negative 9.8, and then delta X here in the diagram is 8. So if you plug all that in your calculator, you should get about 62.72. So as you can see here, up here, we said VI squared earlier. Watch what I'm circling with my cursor. It's about 62.75. Here, using the strategy, I got about 62.72, which is pretty much the same value. Give take a little bit of decimal rounding. So if you want, you can take the square root of that, and on your calculator, it will give you 7.92, which is the same value I said did. So there's a couple different strategies to get there. All right, but now that I found what VF is, all right, so the initial velocity for the second segment is my final velocity for the first collision segment. So I know everything. I'm just gonna plug in here mass of the bullet and mass of the wooden block is just 0.204. And then VF here is 7.92 because I just found that. And then the mass of the bullet is 0.004 thousand kilograms. So if you simplify all this on your calculator, you should get a value of about 404 meters per second. Okay? All right, stay nerdy, don't be whack. I hope my calculator was on point.